focused on Atlantic-basin storms, including how they're forecast, an assessment of their long-term variations, and also mitigation efforts after storms, how we communicate risk and sort of how people deal with that, the aftermath of storms. So the panel is going to discuss the importance of observations and numerical models in forecasting storms, including an assessment of how our observations and modeling strategies might be improved in the future, and what research is needed to facilitate this progress. Finally, we will discuss how the public receive and react to information during an evolving event, and also their migration and sort of movement in and out of areas post-event. So we're missing one panelist currently who had to teach on the downtown campus, but she'll be joining us if she's able. Maybe this is now. Or not, but we should leave the door open. So we have one more panelist who will be coming in. She had to teach on the downtown campus. But briefly, I will just introduce our panelists, and then they'll start with their introductory remarks and/or PowerPoints that they presented. So we'll start on the end with Kevin Reed, who's an assistant professor in the department or in the School of Marine and Atmospheric Sciences at Stony Brook University. Next to him is Maria Mora, who is an associate provost for academic affairs and professor of economics at the University of Missouri in St. Louis. Next is Stephanie Stevenson. She's a tropical applications developer at NOAA's National Hurricane Center, and also a research scientist at the Cooperative Institute for Research in the Atmosphere at Colorado State University. She's also my former PhD student, so I'm very proud to have her here today. Also, the fourth panelist is Rosamar Rios-Barrios, also a product of our department here at the University of Albany. Currently, she's a scientist one at the National Center for Atmospheric Research in Boulder, Colorado. And our fifth panelist is Amber Silver, and she's an assistant professor in the College of Emergency Preparedness, Homeland Security, and Cybersecurity here at the University of Albany, and so she'll be joining us shortly. All right. So the panelists were asked to prepare a few slides, sort of introducing themselves, their research, ideas that sort of fit into the overall theme of our panel today. So Rosie, since you're closest, do you want to lead us off? I don't know how we want to do this. I think most, well, yeah. Oh, so here is our fifth panelist, Amber, that I introduced. Yeah, I think maybe, well, if you want to, you can probably advance it from over there, but if not, just let me know. Is this on? I think it is.
I'm losing my voice, so I need the microphone. Good afternoon, everyone. So it's truly a pleasure to be back in Albany, and so I thank the organizer for the invitation. So for the panel today, I chose to focus on the topic of prediction, and in particular a tool that we use for prediction, which is computer models. And because I realized that not everybody here in the audience knows what a computer model for weather and climate prediction is made of, I thought I'd start just with a brief crash course on it. And in a nutshell, a computer model that we use for weather prediction or for climate predictions is made up of three main components. So we need lots of equations that come from Newton's laws and the first law of thermodynamics, and those equations are solved for many, many points around the world. And because we cannot have infinite points around the world, we wish we could, but we can't, we partition our atmosphere into what we call grid boxes, and the smaller those grid boxes, the finer the resolution and the more details we get, but also the more expensive the computations become. And so that's a theme that's going to come up later on. So I wanted to explain what we mean, meteorologists, by when we talk about model resolution. And there's a third component, and that is some approximations, that even the best models out there don't have all the details, or don't have small enough boxes to be able to see the details of processes that happen very fast at very fine scales, and we call those approximations and parameterizations, and that will come back again. But these models solve equations and give us products that we use for weather prediction, for predicting things like this morning's snow, but also to predict hurricanes and hazards associated with hurricanes. And one of the examples that I want to use to illustrate the current state of our weather prediction models is Hurricane Maria. So this is a famous graphic from the National Hurricane Center showing the projected track of Maria, and this was even before Maria formed. And so this image speaks about the successes of numerical weather prediction models, because even before Hurricane Maria formed, we knew that something was going to get very, very close or over Puerto Rico. What we didn't know, however, was how strong it was going to be. So at this point, we have an H over Puerto Rico, that's a hurricane. They were projecting a category 1 or 2 hurricane. And that's the information that numerical weather prediction models were giving us. So this is an example of the famous spaghetti plot showing tracks or projected tracks from one model run many, many times. And all of the tracks were contained very close to Puerto Rico. For those of you from Puerto Rico, it's not detailed enough because it's not telling you which municipality is going to be affected the most, and that's some information that the public wanted then. But it is detailed enough for us because for us meteorologists we recognize that there is uncertainty and this contains that uncertainty. But you see a lot of orange, that was about category 2 hurricane. In essence, what happened was a high-end category 4, and this illustrates what we know about the current state of weather prediction in terms of hurricanes. And when it comes to the models, we can do very well at predicting where the cyclones are going to go, because that's mostly driven, we think, by currents, air currents that span thousands of kilometers, and that our models and the grid boxes that I showed can resolve. But the processes associated with intensity and the impacts are happening at much, much finer scales. And speaking about the impacts, something that has been, in my opinion, underestimated or underappreciated is that Hurricane Maria brought a lot of precipitation to Puerto Rico, and that caused a lot of domino effects because a lot of the roads were washed out, and then the response was delayed on top of everything that happened. But this is an example again of how our prediction stands at the moment. The prediction was for about 12 to 18 inches, when in certain locations there were over 40 inches. And the graph on the right shows that Hurricane Maria became the record setter for the hurricane that brought the highest amount of precipitation to Puerto Rico. And this was, of course, not forecast. It's very difficult to forecast, as well as how strong the cyclone is going to be, because we can take a look at Hurricane Maria, and as expansive as it is, we believe that processes like rainfall and intensity depend on teeny tiny processes that cannot be seen very well with the current state of weather prediction. So where do we move forward? One way to move forward is to take the best of the two worlds, to take the global models that are able to tell us where the cyclones are going to go, but to make them have fine enough resolution, small enough grid boxes that they can give us enough details to move from where we are now with our current climate models and operational models, moving into storms that look more realistic and that can give us more information in terms of the hazards associated with hurricanes. So that's my vision, and that's also something we're working very hard at where I work at the National Center for Atmospheric Research. So that's all I have.
Thank you, Rosie. All right, Stephanie, do you want to? Sure. Is it here?
No, you can just click on the PowerPoint logo there, which yours is the one on the right.
All right, so as Kristen mentioned, I'm a research scientist at the Cooperative Institute for Research in the Atmosphere, but my office is actually located at NOAA's National Hurricane Center, and I do satellite product development for them. So today I kind of want to just give an overview of the current tools that we have for forecasting hurricanes, some of the products that are put out as a result of those forecasts, and some future directions of where things are heading. So this graph here shows some of the forecast tools that hurricane forecasters have available to them when they're making their forecasts. On the left are observations, like kind of a timeline of when we've had these observations and how they've evolved over time. Satellite data is critical for hurricane forecasting. It's one of the primary observations over the oceans. We don't have as many obs over the oceans as we do on land. Geostationary satellites in particular, we recently just launched a new series of satellites in the United States called GOES-R series. GOES 16 and 17 are now providing us with a lot more data than we've ever had before at a lot finer resolution, both temporally and spatially. But other satellites are also important. We have polar orbiting that provide us some information on storm structure. We have scatterometers that can give us a sense of how strong the winds are at the surface. And another important observation that we have are aircraft data. Of course, these don't always happen, but usually when storms are threatening land, we have planes flying into the storms, both from our military. The Air Force has these C-130s that fly into the storm, and NOAA has research aircraft that they fly in. This is one of them, the NOAA P-3. They also have a G-4 aircraft that flies in the environment. These aircraft carry a lot of instruments on them and can provide us information of where storms are, where the surface center is located, information about how strong it is. They have a variety of instruments on them, such as dropsondes that provide a profile of the atmosphere and some of the surface pressure estimates. They also have radars on them, particularly the NOAA aircraft have a tail Doppler radar on them that gives a 3D structure of the storm. And just last year we were able to provide this data to our forecasters in real time so they can kind of get a real-time picture of what the storm looks like in 3 dimensions. There's also a lot of other data, as you see listed here, ships, buoys. When it's close to land, radar is obviously important. There's just a variety of observations, but satellite and aircraft are the 2 primary ones. In terms of model guidance, Rosie just gave us a nice overview of how this works. These are some of what our forecasters have available when they're making their hurricane forecasts, including a suite of global models. The GFS is the American model that was recently upgraded this year to FE3, which is a finite volume cubed sphere model. There's also a suite of ensemble models. Rosie showed us a plot of what one of those looked like in terms of intensity forecasting. And then there's also regional models that are more on the storm scale, such as HWRF and HMON. As we move into the future with our US models, they're going to be directing these towards a core that's very similar to the global model, the FE3. So kind of unifying a lot of these ensemble, regional, and global models into one core is a direction that NOAA is heading in. There's also some statistical models. These are primarily, I would say, used for intensity. SHIPS and LGIM are 2 of the popular ones listed here. Until recently, when our regional models had higher resolutions, these were actually our top skillful models in terms of intensity prediction. Since model resolution has increased, regional models have started to become better, but forecasters still look at these. And in terms of rapid intensification, this is one of the biggest problems that plagues the hurricane community. RIAs are still beating out what our numerical weather models can do. So there's a couple of them listed here, and there's a lot of development in this area predicting rapid intensification. And then consensus aids listed here. A lot of times forecasters won't rely on any one model output. There's consensus aids that combine the models into a preferable, or based on historically what happens, which performs better, can provide a better estimate of track and intensity. So looking at how tropical cyclone products that we put out to the public have evolved over time, back when the Hurricane Center started, they only provided 2-day forecasts. Right now, there's 5-day forecasts available. Internally, 7-day forecasts are produced, but those aren't available to the public yet, and I think there's still a lot of work. We still have a lot of track air out at 7 days. Watches and warnings are available out to 36 and 48 hours. Right now, Hurricane Center puts out wind and storm surge watches and warnings. 2019 was actually the first year that our storm surge unit at the Hurricane Center had the ability to issue a storm surge watch or warning for Puerto Rico and the U.S. Virgin Islands. So that's a major advancement that's happened that can help potentially save lives in the future. Speaking of storm surge, there's potential storm surge flooding maps that are available. Wind speed probabilities provides a nice graphic of the probability of getting tropical storm or hurricane force winds at a given location. And last year also a time of arrival graphic went live, and this is a very nice product that can allow the public to know when can I expect those winds to come. Gives them some idea of when they should maybe have their preparations finished before the storm arrives. A variety of Outlook products, text and graphical outlooks. If you go to the main page, you can see the probability of formations in yellow, red, and orange circled areas that they're watching. There's text products, the cone graphic that we just saw. Social media and key messages have been two things that have come up recently. NHC really likes to use social media. This year they took Facebook Live and did a lot of Facebook Live sessions trying to provide a more personal experience with the forecast to the public. And key messages I think have also been important in communicating the hazards and forecast uncertainty that maybe isn't available in some of the other products. And then within the last decade, we have potential and post-tropical cyclones. As Rosie showed with Hurricane Maria, that was a potential tropical cyclone that they knew was going to form. This allows them to provide warnings ahead of time so that people can prepare even though it might not have the tropical characteristics yet. Or after the storm finishes, they can still have surge effects that the public needs to know about. So this graphic is just showing the last 3 years. We've had a lot of major hurricane impacts in the Atlantic-basin. Harvey along the Texas coast in August of 2017. Irma skirting across the Caribbean, hitting 7 different locations of land throughout the Caribbean and Florida. Maria making landfall in Dominica and Puerto Rico. Michael last year in the Florida Panhandle, and just this year Dorian in the Bahamas. So this is just highlighting some of how the key messages can be used to communicate some of those threats. You can see in this one from Harvey, they mentioned heavy rainfall. Of course, that was one of the major impacts. From Maria, you can see one of them at the bottom here, life-threatening flash floods and mudslides from heavy rainfall. So even though the number might not have been right in terms of the predicted amount of precipitation, they're able to get the message across that that's something that they're concerned about. And lastly, moving forward, I'm not sure if anyone's heard of the Weather Research and Forecasting Innovation Act of 2017. This was passed by Congress in April of 2017 before our terrible hurricane season. But Section 104 of this calls upon NOAA to maintain a project to improve hurricane forecasting. And they call out 3 things here, and I think these are the areas that we need the most work in right now. The prediction of rapid intensification and track of hurricanes, the forecast and communication of storm surges and hurricanes, and risk communication research to create more effective products. So a team of scientists that are part of this hurricane forecast improvement program created goals that we're going to track over the next 5 years as part of the strategic plan to address what this Weather Act calls upon. You can see what some of them are here. Rapid intensification being important, 7-day forecast guidance, improving that so that we can move towards having better lead times. Improving genesis timing. We saw some errors with that this year with Imelda making landfall in Texas 2 hours after it formed. There's still some work that we need to do in terms of properly understanding when storms will form. And then risk communication. This is something that the atmospheric science community is really moving towards, working with social scientists and really trying to figure out how to communicate the science better to the public. So that's all I have.
Thank you, Stephanie. I think maybe it makes more sense to maybe go with, Kevin next. So.
Okay. I'm going to probably have to come over and stand over here because it's not going to switch, right?
Okay.
Did you say it's over here?
Yep. And then I think you can go to the last one and show it as this large screen.
Okay, awesome. So I broke the rules and didn't do a PowerPoint because normally when I do the Mac conversion to a PC for PowerPoint, I normally get destroyed, and so now I put it in a PowerPoint or a PDF, and now it's not working. But I thought what I would do is talk a little bit how we do this, how we look at future North Atlantic tropical cyclone seasons from the standpoint of climate modeling. And so it's perfect to go after Rosemar because she kind of gave me already a nice introduction to at least how we use our numerical models. And so it's a very similar approach, right? We're using atmospheric models, but the difference that we're doing between kind of the forecasting and the climate scale is actually just your temporal, right? So how long are you going to run your model for? And so in the forecasting community, you're maybe running your model for 7 days, or maybe sometimes you're doing some seasonal forecasting. But in the climate community, what we're actually doing is we're running our model for maybe 30 or 40 years. And so it's orders of magnitude difference in terms of computational costs that are required. And so because of this, we're a little bit behind in actually trying to reproduce the perfect structure of these storms that Rosemar, I think, did a good example of showing how as you increase this grid, or decrease this grid spacing, or increase the resolution, the grid boxes, you increase kind of the realism of your storm. And so what we do is we take kind of what we would call a current state-of-the-art climate model, which is typically run at very, very coarse resolution of 100 kilometer grid boxes by 100 kilometer grid boxes, which means if you run this simulation for 30 years, and you look at the number of hurricanes that you get in that data set, you can barely see them on this plot, and that's because there's about maybe 2 or 3 a year, and they take very weird tracks. And that's kind of expected. You wouldn't expect to resolve the details of the storms at those resolutions. But if we kind of go to what I refer to as advanced climate modeling, this is kind of the next generation of pushing our climate model to be closer to the spatial scales that exist for weather models. And so if we go to 25 kilometer grid spacing, so a 4 times decrease in the grid space size, but a significant increase in the computational cost, you can actually see here just from this graphic that the number of hurricanes actually increases dramatically. And so we seem to cross a pretty important threshold that's required to actually simulate these storms. And so this suggests that maybe we can use these type of tools to project future tropical cyclone counts. And one of the ways we do that, and this is what I refer to as kind of the typical climate approach, is we run a 30-year simulation in the current climate, and we run a 30-year simulation from 2070 to 2100 under these projected RCP scenarios that come out of the IPCC. And then we look at storm counts globally. Okay, so this doesn't really attack the question that we're kind of answering here in this panel discussion, which is how do we project and prepare for future hurricane seasons. But this is kind of the typical climate way to look at trends, and you can compare the number of storms in reality, the number of hurricanes compared to the number of hurricanes in the future simulation, and you can see that we project a decrease globally in the number of hurricanes, but a significant increase in the major number of hurricanes. However, this again isn't that useful, at least in my opinion, because it doesn't actually provide you anything about regional, and it doesn't actually provide you anything about the hazards associated with the tropical storms, right? You're not necessarily, if we saw a significant increase in category 4 and 5 storms, but I was able to show you that none of them, or the likelihood of landfall decreases significantly, then the impact on society is not as clear. And so what we try to do at Stony Brook is we try to focus actually on a kind of a hazards approach. So what we try to do is when we project to the future, we try to look at what's the change in extreme precipitation that comes from tropical cyclones. And maybe that's one way to look at potential hazards. And so what this just shows you is it's just a metric for extreme precipitation in the United States. It's basically the annual maximum 5-day accumulated precipitation. So we just look at, we look at 5-day periods and see what's our largest event for the year. And the reason we're choosing 5 years is because we're actually trying to pick up these events like Hurricane Florence and Hurricane Harvey, which dumped a lot of precipitation over a few days. And what we can do is, if you just focus all the way over here on the right, as you can see, is we've come up with a way to look at the percentage of those RX 5-day events, those extreme precipitation events, let's call them that are due to tropical cyclones. Because if you want to look at trends and how tropical cyclones change in the future, you might be interested in not necessarily knowing if it's a count change, but is the likelihood of your extreme precipitation along the eastern United States coming from tropical cyclones, is that increasing or decreasing? And that allows you to maybe prepare as a water resource manager from a different perspective of, well, we know that the events, we know that the characteristic of an extreme event from precipitation that comes from a tropical storm is different than maybe your run-of-the-mill summer convection. And if we can at least start to project differences in that breakdown, then maybe water resource managers can use something based upon how they currently plan to change the way they plan for the future. And then another way in which we're trying to do this, which is actually to use a more kind of what we refer to as a conditional attribution methodology. And so one of the ways to do this is we can actually take our climate model and we actually treat it like a weather forecast model that we saw in the last 2 introductions. And so one of the ways we can do this is we can actually set up our climate model. We set it up very similar to how you can set up a lot of weather forecast models now, which is this high resolution domain, this high resolution over the area of interest, in this case the North Atlantic. It's conveniently over the North Atlantic. And we can actually run forecasts. So we outsource all of our data simulation. So the hardest part about running a forecast, we outsource it to NOAA, and we take their initial conditions and we put it in our climate model, and we can run our climate model as a forecast model, because in the end they're the same kind of numerical tools. And we can run our forecasts, and we can run 100 ensembles, and then we can do the same thing in which we run a counterfactual forecast. And this is actually in which we run the same exact storm, but we remove the large-scale climate change signal to date. And the reason we can do that here is because we're actually running a climate model, which means conveniently we can also run the climate model for the last 100 years without greenhouse gas forcings, for example. And then we can reinitialize our model for our forecast of our individual storm, and we call this the counterfactual forecast. And the reason this is unique is because it allows us to use a storyline approach, right? So I'm going to show you an example here with Hurricane Florence, but this could be done for any hurricane that's occurred in the last decade or so. And what we do is we run our simulation, 100 ensembles with and without climate change in the initial conditions. And then we can actually compare those differences in things like rainfall. This is the mean rainfall across the whole ensemble set. But if you just kind of focus on the colors, you'll notice that in the actual forecast, the real forecast, there's actually a pretty substantial increase in the precipitation associated with Hurricane Florence. And what this actually suggests when you break that down in statistics is that the extreme rates and the total overland precipitation, for example, within Hurricane Florence is statistically increased by 4 to 5% because of climate change. And so this is one way in which we're trying to communicate not only the impacts of climate change during real events that have happened, as opposed to kind of the first approach, which is we expect a decrease in the number of storms in the future, but maybe an increase in the major storms, is to try to relate it directly to storms. But it also allows us the ability to use those storms as areas rebuild after a storm. Often, the common thing to do is to say, okay, this storm happened, so we're going to rebuild so this storm doesn't happen again. But what you have to realize is that if you do that, you have to actually assume that you can use the same methodology to run what this storm would have looked like maybe in 2050 or 2100, which actually allows you a direct methodology to actually develop your resiliency for future expectations of what that storyline, what that storm you're planning for actually might be changed. And so with that, I'm done.
I'm also going to stand up. I have a hard time sitting down and talking sometimes. Well, good afternoon, everybody. I want to start off by thanking the organizers for having included me in this panel. It's very exciting because we do have a truly interdisciplinary group here today. I'm going to be talking about how we can bring in the social sciences in terms of thinking about characteristics of building communities and keeping up with that resilience. So I'm a professor of economics, and I've been collaborating with other economists and also sociologists. And we have a political science professor here, who I've also worked with over the years. So when we consider what are the best ways that we can respond to the needs of incoming migrants, I'm looking at this more from the communities in the receiving areas. And one of the things that we can consider is looking at social science to consider what the characteristics are of migrants that have recently gone before, let me say pre-disaster. So migration patterns, if we consider, are not going to be a random event. And post-disaster migrants may be tapping into the recent pre-disaster migration networks. And that's something that my ongoing work with Avilan Rodriguez, who is the president here at University of Albany, SUNY, so very proud of him, and also Alberto Dávila, who's at Southeast Missouri State University. We've been working on issues related to Puerto Rico actually for about 8 years now. It was going to start off as a book chapter, and it just began evolving much more. And so we have a book, we have several journal articles, etc. In fact, the presentation I have here draws from a variety of our different works, but one of them is our book. We have a book that came out in 2017, November. We got the galley proofs for this book literally 2 days after Hurricane Maria struck. And so we begged our publisher to let us have an addendum. Normally they don't like you to change anything, but they did give us, so we have 3 paragraphs, so they're long. But we talk about but we talk about how we can use the information we have in our book moving forward, because we already knew it was going to be a major storm, a major catastrophic storm. And one of the reasons why we knew there would be such devastation across Puerto Rico is because we had been studying the island of Puerto Rico and a lot of the pre-Maria migration patterns. It should be noted that more than before Hurricane Maria struck, Puerto Rico was undergoing a deep, severe economic crisis that had been surging since 2006. And so as a result of the crisis, and we talk a lot, I'm not going to go through the details about what were some of the stimulants behind that, but as a result, there was a huge out-migration that people just weren't talking about. And so when thinking about a storm like Hurricane Maria, you're going to expect to have some out-migration. We had been studying a lot of the characteristics of the migrants from the island to the mainland using the American Community Survey and other data sets. And then we also have information on actually people who moved back to Puerto Rico using the Puerto Rico Community Survey. We were very pleased that our book did have a 2017 publication date because we wanted it to be 100 years. So 1917 is the year that the Jones-Shafroth Act was passed, and that collectively granted Puerto Ricans U.S. citizenship. So what we thought was very ironic is 100 years of U.S. citizenship. Here was a territory of the United States, a Commonwealth actually, that had been undergoing the severe economic crisis that only had 1 year of positive economic growth since 2006, and that was way back in 2012. So then, again, this was all happening before Hurricane Maria. The hurricane ended up exacerbating what we started referring to as La Crisis Boricua. Some people have also referred to this time period, the 2006 onward, as being Puerto Rico's depression, and that is not an understatement. Whenever I give these presentations, including in Puerto Rico, I always have a slide about why the U.S. at large should care. We would hope people would care, even just for basic humanitarian reasons. But of course, Puerto Ricans are U.S. citizens by birthright. They also represent a significant population of almost 9 million if we add people on the island as well as individuals who identify as being Puerto Rican who are living on the U.S. mainland. And if you don't think 3.2 million is that big, it's important to note that there are 21 states that do not have populations of 3.2 million, and nor does Washington, D.C. So the presence of Puerto Ricans on the mainland have actually been increasing, including in some non-traditional areas like Texas. And I'll show very quickly some of the where the migrants are going. Florida has emerged as being like the big, I guess you said like the big winner in terms of receiving many of the migrants, both pre and post Maria. And the longer it takes this crisis to address, the longer it's going to be the cycle of more out-migration, the demographic shift, economic decline, and of course human suffering. To give you an idea about some of the estimated net out-migration before Hurricane Maria, so these are our estimates based on U.S. Census Bureau data between 2006 and July 1st, 2017. They do their population estimates as of July 1st. So this was just a couple of months before Hurricane Maria, and we estimate that Puerto Rico had lost due to net migration about 600,000 people, which represented about almost 16% of their 2006 population. In terms of actual numbers, this is the largest out-migration or net migration that Puerto Rico had experienced. Relative to the size of the population, it is the second largest when we go back to the Great Migration of the 1950s. But since Hurricane Maria, our colleagues at the Center for Puerto Rican Studies, Centro at Hunter College, estimated that just within the 6 months after Hurricane Maria, that another almost 136,000 people had left the island for the mainland. And so we're looking at well over 700,000 people who have left the island for migration purposes. And that is getting to the Great Migration period in terms of representing about 1 out of every 5 people in Puerto Rico in the year 2006. So where are people going? So I was saying this kind of looks like saltwater taffy when I put this in PowerPoint. These are the main receiving states. So Florida is the state that has received the highest share of the migrants. And this is our estimates up to 2016. Florida has received